let G be a group acting transitively on a locally compact Hausdorff and second countable topological space X. And let mu be a G invariant Borel probability measure on X. And finally let F be a sub-semigroup of G acting ergodically on the probability space X mu. And then we have, for mu almost every X in the topological space, we have the orbit of X under this subsemigroup is dense in X. Hey guys, today we are going to talk about a very important theorem that I frequently use in my research. Suppose you have a group acting transitively on a nice topological space, and you have a measure that is in probability measure that is invariant under this group. And if you have a subsemigroup that acts ergodically on this space, then almost all orbits under this subsemigroup is dense in the topological space. And now let's start proving this. First, let's take the exceptional sets, namely the sets of points in X where f dot x is not dense in X. And our goal will be to prove that S is mu null. But it is hard to prove this directly. How do you put S into a set of measure 0? So instead, the idea will be to put S into a countable union of mu null sets, and use the subadditivity of measure to conclude that S is mu null. So here's a place where we need the second countability of the topological space X. So now since X is second countable, we have that there exists a basis denote the u sub n, where n ranges from 1 to infinity of X, and each u sub n is an open subset. Now for each n greater or equal to 1, we let a sub n to be f inverse acting on u sub n. And by definition, this means the union of all elements in F of F inverse dot U sub n. And here are some quick observations. First, we have F inverse dot an is always contained in an. This follows from the fact that F is a subsemigroup, and multiplicativity is preserved. And second, mu of F inverse dot an is always equal to the mu of an. This is because that by our assumption, mu is G invariant, and F is a subsemigroup of G. Mu is G invariant. And the third observation is not so obvious. The mu of an is strictly greater than 0. This is because when we take the basis, we usually implicitly assume that each basis element is non-empty. And as a result, because U sub n is non-empty, we have mu of un is strictly greater than 0. And since the identity element is in F, U sub n is contained in A sub n. So that is why mu of an is strictly greater than 0. And now you might want to ask, why does mu of U sub n is strictly greater than 0? That's a very, very good question. I'll leave a question mark here and I will explain it later, because this is not so trivial. Let me first tell you what 1, 2, and 3 will tell us. 1, 2, and 3, together with the ergodicity of F action on X, tells us that mu of each A sub n must be equal to 0. And this is essentially the definition. So here we are essentially using the definition of the ergodicity. And this guy further implies that mu of the complement of an is equal to 1. Implies that mu of A sub n is equal to 1. And this further implies that the complement of an has measure 0. Remember at the beginning when we talked about the idea of the proof, we said we want to put S inside the countable collection of subsets of mu measure 0. Now we have found the subsets we want. Now we consider the union of all complements of A sub n. By the subadditivity of the measure, we know that this guy still has measure 0. And note that this part is equal to the complement of the intersection of all those A sub n's in X. And we claim for every X in the intersection of those A sub n's, its F orbit is always dense in X. This is because for any x in this intersection, by definition of A sub n, definition is here. For each n greater or equal to 1, U sub n intersection f dot x is non-empty. This is because since x is in A sub n, there must exist an element f in F such that F inverse dot un contains x. Or in other words, f dot x is in U sub n. Or in other words, f dot x is in U sub n. And now we have verified this claim. But U sub n's form a basis for x. And this verifies the density here. And this proves the claim as well as the theorem. But wait, there's something we haven't addressed yet. We haven't answered the question why the mu of U sub n is always strictly greater than 0. So the proof is not finished yet. To verify this, we need to verify another claim. Claim mu of U is strictly greater than 0 for every non-empty open subset U of x. Remember that x is locally compact Hausdorff and second countable. Actually, we haven't seriously used the locally compact Hausdorffness in our proof. And here's how we're going to use it. There's a theorem in the real analysis by Folland. This is a theorem 7.8 in the page 217 of the real analysis by Folland. And this is a second edition. Part of this theorem states that every Borel measure on a locally compact Hausdorff and second countable topological space X that is finite on compact sets is regular and hence random. In our case, since mu here is a Borel probability measure, and in particular mu is finite, so the conditions of that theorem is satisfied. So the conditions of that theorem are satisfied. And we do need the locally compact Hausdorffness and the second countability. What we need in verifying this claim here is the regularity of the random measure. Because now we have that mu is radon by the inner regularity of radon measures applied to the whole space X. We know there exists a compact subset K of X such that mu of K is greater than 0, because mu of X is equal to 1. And here we need the transitivity of the action. And by the transitivity of the action of G on X, we know that the union of G dot U, where G ranges in the group G, forms an open cover of K. And by the compactness of K, we know that there is a finite subcover. Now it follows that we have the following inequality. This mu of K is greater than 0, which is less than or equal to the mu of this finite union. And by the subadditivity of the measure, this is equal to the finite sum from k equal to n of mu of g sub k of u. But by the G invariance of the measure mu, this is equal to the summation of mu of u, which is n times mu of u. Because n is a finite number and this mu of k is greater than 0, we finally have mu of u strictly greater than 0. That finished this claim, and finally, this is the end of the proof.